going to introduce two important and interesting security challenges in software development and how we can use static analysis tools like CodeQL to identify and address these issues before they become bigger issues. So my name is Tong, and I am a software engineer at the Microsoft Security Code Analysis Platform team.
And my name is Asha. I'm on the same team as Tong.
Let's pause for a moment and imagine ourselves in year 2035. What is the life you expect? Flying cars, humanoid robots? Well, I don't know, but there's one thing for sure. Technologies will undoubtedly evolve at an even faster pace than we expect. However, there's one imminent challenge that we need to prepare for now: Q-Day. So the name sounds cute, but the concept is quite a bit scary. The Q stands, here stands for quantum. So everyone has heard of quantum before. It's not just some vague sci-fi or spiritual concept. It's real and it's coming. So Q-Day refers to the moment when quantum computers become so powerful enough to break the cryptographic systems that's protecting our cyber world today. Many experts believe that Q-Day could arrive as early as the next 10 years. In fact, the National Security Agency has set a 2035 deadline for adopting Post Quantum Cryptography (PQC) across all national security systems. So why quantum computers are so powerful? Well, traditional computers use bits, and these bits are binary, meaning that they can be either 0 or a 1. Think of flipping a coin. So in classical computing, you flip the coin, and it lands either heads or tails. One outcome, never both. Well, in a very unlikely scenario, the coin might land on its edge. And if that happens, you should probably go buy a lottery ticket. But even then, it's still neither heads nor tails. In quantum computing, however, flipping a coin is not an OR logic relation, but rather an AND relation. So imagine the coin spinning in the air, existing as both heads and tails simultaneously. This is a state called superposition, which gives quantum computers a massive advantage in processing speed because they can handle multiple possibilities at the same time. Now, the ability doesn't come easily. So to maintain a qubit superposition stability, quantum computers need incredibly controlled environments. So devices like dilution refrigerators can keep quantum computers at temperatures as low as 2 millikelvin. So it's colder than the deep space. It's the coldest place in the universe. So this together gives quantum computers the ability to crack encryption easily. So the most popular cryptography used in security communications nowadays is asymmetric encryption. It encodes and decodes messages using a pair of mathematically linked public key and private key. So imagine Bob wants to send a message to Alice. Unlike in symmetric encryption, where both Bob and Alice share the same key, in asymmetric encryption, we use a pair of public and private keys. So Bob will use Alice's public key to encrypt the message before sending it to her. So this encrypted ciphertext is sent to Alice over a public channel. When Alice receives it, she used her paired private key to decrypt the message. The important point here is that even if someone intercepts the ciphertext along the way, they cannot read it without having Alice's private key. Bob knows Alice's public key, which anyone can know, but only Alice has the corresponding private key, so not even Bob can decrypt the message. As long as the private key is kept confidential, the data exchange is secured. But is asymmetric encryption truly safe forever? I'm going to use RSA as an example to explain. It's a very common, fundamental, and widely used asymmetric crypto system. Let's first look at why it was considered secure, and then see why it is going to be in danger if Q-Day arrives. So RSA is an example of trapdoor function, which means that it's easy to compute in one direction, but extremely difficult to reverse. Imagine multiplying two prime numbers, for example, 53 and 61. It's easy to calculate the product even manually, which is 32, 33. But if I give you a large enough number and ask you to figure out which two prime numbers were multiplied to get this result, it will be extremely difficult. What you see here on this slide is a product of two large prime numbers. So factoring this 24 bits long number could take 1,000 years, even with the most powerful computers we have today. This is the backbone of how asymmetric encryption like RSA works. RSA relies on relatively simple mathematical concepts, prime numbers, what we just talked about, and modular arithmetic. I'm not going to cover all the math here, like how the equation is derived, but it's pretty straightforward. So if you're interested, you can also probably deduce the formula on your own. What I want to highlight here are the two keys we just mentioned. So the public key consists of two components. The modulus n, which is the product of two large prime numbers, p and q, that are kept secret, and the public exponent e, which ensures efficient encryption. The private key, on the other hand, is represented by the value d. So in simple term, it's calculated in such a way that it undoes the encryption done by e. So the security of RSA relies on the difficulty of factoring the large number n to get the two prime numbers p and q. Without knowing p and q, finding d, which is the private key, from e, the public key, is computationally infeasible. So RSA is powerful and has been widely used to secure the world for many years. But how do quantum computers threaten this? And why is RSA no longer considered fully safe when Q-Day arrives? This is where Shor's algorithm comes in. I'm not a quantum expert, so again, I won't cover all the math and physics details behind Shor's algorithm, but I will try to explain it briefly. So Shor's algorithm was developed by the American mathematician Peter Shor in 1994. It is a quantum algorithm for finding the prime factors of an integer using quantum Fourier transform, QFT. The QFT is a key step where the algorithm finds the period or the pattern in numbers. Quantum computers then can use the characteristic of superposition we just talked about to explore many possibilities simultaneously, so they can find these periods or patterns really quick. Once the pattern is found, it's used to factor large numbers, which breaks the RSA entirely. This ability to factor a large number quickly is what makes Shor's algorithm such a threat to modern encryption systems. RSA encryption depends on the assumption that factoring large number is hard, but Shor's algorithm drastically reduced the time that's needed to factor them using a quantum computer. So then you may want to know what is the recommended key length for RSA in PQC practice. As you can tell already, RSA key length affects the levels of security. In this diagram, you can see that as the length of the RSA key increases, the security level also increases. N-bit security, for example, 80-bit security, means that the attacker would have to perform 2 to the nth, which is 2 to the 80th operations to break it. Therefore, obviously, longer keys will in general be safer. The recommended length, however, is a tricky question. The standards are changing fast, so I want to be cautious, and I'm not saying anything for sure here. Just to give you some insight, I'm showing you the CNSA guidelines. The CNSA, which is the Commercial National Security Algorithm Suite, is a set of cryptographic algorithms promoted by the National Security Agency. And in CNSA 1.0, which is the current standard, a minimum of 3072 bits RSA key is suggested. However, in the proposed future standard, CNSA 2.0, it removed RSA entirely and suggests that it should be deprecated at that time. I've linked some helpful resources at the end, so check it out if you want to know more about the latest updates. Shor's algorithm presents a serious challenge to not only RSA encryption, but also other encryption methods. I'm quoting Arthur Herman, who is the director of the Quantum Aliens Initiative, that Q-Day is likely to come sooner than even quantum scientists can predict. And the time to get ready to protect our vulnerable data and networks is now. We need to prepare for this quantum-safe future by considering post-quantum cryptography practices that can resist quantum threats. One of the key preparation methods we want to introduce here is through static code analysis. The security standards are changing fast. We now have stricter rules for protecting data, but a lot of the older legacy code, or even the code we currently write daily, hasn't been updated to meet these new standards yet. It's very difficult to check manually where these vulnerabilities are in our source code. So static code analysis is important in software engineering. It is a method of analyzing computer programs without executing them. It examines the source code to identify potential bugs and security vulnerabilities early in the development process. Unlike dynamic analysis, which requires running the program, static analysis evaluates the code structure, syntax, and logic. In simpler terms, it's like proofreading code before it's even running, so that people can catch mistakes like outdated encryption methods, hard-coded credentials, or logic errors that could lead to bigger issues down the line, making software more secure and reliable. Let's take a look at some popular static analysis tools. You may have heard some of them before. For example, Roslyn and Prefast are very lightweight tools that's fast and doesn't require build to run. But they only support C# and C++ respectively, and the scope is limited. Roslyn can only catch 3 flow steps, and Prefast is limited to the function level scope. I will talk more about what flow steps mean later and why it is important in static analysis. SamGrep is also lightweight, and it supports most coding languages and frameworks, including snippets. However, it only covers file-level scope and has limited semantics. Sonar Cloud offers great multi-language support and CI/CD integration. It's cloud-based, so it's easy to set up and integrate with various pipelines like GitHub or Azure. However, Sonar Cloud is a paid service, and it's not that powerful on deeper security analysis. CodeQL is a free semantic code analysis engine. It's acquired and now maintained by GitHub. So Asha and I are not on the product team, but we use and maintain CodeQL a lot in our work for static analysis. CodeQL supports full and thorough semantic analysis and can trace data flow across the global scope. So it's great for identifying complex vulnerabilities like SQL injection, cross-site scripting, or buffer overflow. The downside of it is that the learning curve is steep, so it can take some time before writing complex queries. It can also be slow on large code bases. If you compare these options, lightweight tools like Roslyn or SamGrep are great for quick surface-level checks. They can also be easier when writing custom queries compared to CodeQL. CodeQL, on the other hand, is an overall comprehensive option when it comes to deep security analysis. We will use CodeQL today to illustrate how it can help detect hidden security vulnerabilities, like the bad usage of a small RSA key in code, for example. As you may have guessed from the name, CodeQL combines both code and query language. At its core, it treats code as data. So we can write CodeQL queries, just like SQL queries, to analyze code for issues related to security, correctness, maintainability, and readability. This video shows how to create a CodeQL database in VS Code Terminal. CodeQL CLI extracts relational data from the source code to create a CodeQL database that has the information on how the code is structured. It represents functions, variables, and data flows as queryable data points. So code plus QL lets you query code as if it were data. In the next video, you can see how this database is used when writing CodeQL queries. Here's where the concept of AST, or abstract syntax tree, comes into play. The AST, shown in the red box here, is a tree-like representation of the source code. By treating the code this way, CodeQL allows the users to search their code at scale for complex semantics patterns. User can also customize the queries for specific patterns. Okay, so back to RSA encryption. I want to connect the dots here and show you a practical example of how CodeQL can detect the usage of RSA in the codebase. We have a simplified example here in Go language, where a RSA private key is generated using the standard crypto RSA package. The user specifies the key length as 1024, which was disallowed by the National Institute of Standards and Technology, NIST, 10 years ago, back in 2013. So it's definitely weak, and we should avoid from using 1024-bit keys, of course. So now, if the question is simply to detect any RSA usage, no matter where the key length, no matter how the key is used, we can write a super simple query in CodeQL to detect that. For example, in CodeQL for Go, The call to the wrapbox RSA.generate key is represented as a selector expression, and by having a query like this, any line of code that calls the RSA package will be flagged. You can also see here that CodeQL queries follows the QL structure of having a from where select statement, where the select statement includes the final part alerts you want to create for the findings, such as this usage is bad and please use a stronger key length, blah, blah. Now, I know some of you might be thinking, why not just do a Control F to search for keywords like RSA? Why use CodeQL? Well, one of the reasons is that the example on the previous slide was a super simple code that only has a few lines. Imagine code bases that have millions lines of code with really complex imports, naming, and structures. Searching manually is a very time-consuming effort. A more important reason here is that CodeQL can track the data flow from a source to a sink in the code. You have heard me talking about data flow several times, so here I'm going to explain it a bit. The actual thing we want to catch here is not the keyword like RSA itself, but how the data is flowed in a dangerous way. A data flow usually consists of a source and a sink. A source is where untrusted data enters the system, such as variables, user input, etc. For instance, in our RSA example, the source is a small key length 1024. The data flow ends in a sink, which is where this untrusted or weak data is used in a potentially harmful way. In this case, the small key length is used in the RSA.generate key function as a parameter for generating a private key, which should be flagged because we don't want to use this small key length. Asha is going to talk about tended tracking later, which is a more complex data flow scenario. But in this example, it's pretty straightforward that an integer source flows directly into a function called sink. We can then write a more specific and complex query that utilizes the data flow tracking feature in CodeQL. In this more complex query, we define the source as any integer that's less than 3072 bits long. I chose 3072 because that's the CNSA 1.0 suggested length, but keep in mind that it's subject to change. We then define the sink as the second parameter in the RSA.generate key function call. So CodeQL is then able to track the flow from the green box, which is the source, to the red box, which is the final sink of the source. The syntax might seem weird and not very intuitive. For example, you have 4 columns in the select statements instead of just 1, but don't be scared. That's just how CodeQL is written for showing both the sink and the source in the final alert. This is what you will get by running this query in VS Code. It will show you the bad source and the potential sinks of the source, and also the location info of these information in the file. You can see that the blue 1024 here is a clickable element. So clicking on it will take you directly to the line of code where the RSA key is defined, which is the source. This is also an illustration of why CodeQL is powerful, because you can have the primitive values as an AST node so that you can trace down the entire data flow. For more information on how to start your first query, we have included a resource section with helpful links at the end of the presentation for you to refer to. So I've only scratched the surface on PQC today. My team at Microsoft and some folks from GitHub and Santander Bank have worked on an exciting project that used CodeQL to analyze the security status of the top repos in GitHub to facilitate PQC adoption. You can learn more about this in the blog post linked here or by watching the Black Hat presentation recording about this project. Well, to conclude my part, I guess the takeaway here is that we need to start preparing for post quantum cryptography, but don't be panicked. I don't want to deliver the wrong message regarding crypto, so I'm being super cautious. I know the NIST has proposed a pretty ambitious transition timeline before 2033, and that the final FIPS validated standards for the algorithms are out already. However, some of the work for how to adopt them, for example, combining traditional methods like RSA with new methods like module lattice-based mechanism, is still in draft form. While RSA is not broken yet, we have to assume a cryptographic relevant quantum computer may soon exist, and that we should take the appropriate steps to protect ourselves. In the interim, NIST suggests that CNSA 1.0 compliance, I showed previously, should continue to be required. So let's start by practicing static analysis to check for the weak crypto usage in our code. While PQC raises really big security questions, CodeQL is also a great tool for detecting more immediate vulnerabilities, often seemingly trivial, yet very crucial ones. Next, I will hand it over to Asha, who will walk you through an example of another interesting topic, the leap year crisis, since this year, 2024, is leap year. She will also introduce other fascinating aspects of CodeQL, such as chain tracking or Merva, that will give you more abilities and flexibilities to write your own customized queries.
All right, so to continue on our presentation, I wanted to talk about a technical issue that's been affecting software systems worldwide, what's commonly referred to as the leap year bug. This may sound pretty small or obscure, but this bug has caused significant problems to systems ranging from personal devices to corporate servers. So what exactly is the leap year bug, and why does it matter? To understand the leap year bug, we should probably review the concept of a leap year. As you probably know, most years have 365 days. However, the actual time it takes for the Earth to orbit the sun is roughly 365.24 days, which is known as a tropical year. To account for this extra fraction of a day, we add one day, February 29th, every 4 years. But it's a bit more complex than that. A year is a leap year if it's divisible by 4, but not if it's divisible by 100, unless it's also divisible by 400. For example, the year 2000 was a leap year, but the year 1900 was not. Now, what does this have to do with bugs in software? Many systems and applications are designed to handle dates and times, but not all developers account for the rules of leap years correctly. When software is written without properly accounting for these, it can result in what we call the leap year bug. This bug occurs when systems fail to recognize February 29th, add or subtract days incorrectly, or mishandle dates around those leap years. The most famous case of a leap year bug occurred in 2000, the first leap year of the modern digital age. Some systems treated 2000 as a regular year because they followed the rule that said a year is not a leap year if it's divisible by 100. They completely forgot the exception that it could be because it's divisible by 400. This oversight caused applications to crash, others to display the wrong date, and others to completely malfunction. Issues arose in mainframe systems, financial software systems, and embedded systems like medical technology. For instance, some of the older mainframe systems and financial software systems incorrectly calculated dates, leading to erroneous billing cycles, miscalculated interest rates, and scheduling issues. Though the largest disruption occurred in February of 2000, there are major cases that occur every leap year. I've attached 4 examples of these disruptions here, but we'll be focusing on one of the largest disruptions in recent history. In 2012, Microsoft Azure's cloud platform experienced a leap year bug. Azure is one of the world's leading cloud services, and its outage had a global impact. The problem occurred because a portion of the Azure infrastructure didn't account for the extra day in the leap year. When the system tried to calculate certificates based on date and time, it failed, causing a massive service disruption. As a result, businesses relying on Azure for hosting, data storage, and other services faced unexpected downtime. The outage lasted for over 12 hours, leading to significant operational and financial losses for companies around the world. While that slide showed some of the major, well-known leap year bugs from the past few years, there are security concerns that arise from these all the time. Leap year bugs can cause systems to mishandle date-related data, leading to improper storage or deletion. Sensitive data being lost or leaked due to an incorrect date calculation can lead to breaches that expose confidential information to unauthorized parties. Software improperly allocating memory when handling dates in a leap year can lead to memory leaks, where resources are consumed but not released, degrading system performance and creating openings for attackers to exploit the system. Some security systems rely on time-based authentication tokens, the way that Azure did, and those expire after a certain period. Leap year bugs disrupt the handling of these timestamps, which might cause some users to experience authentication failures and other unauthorized users to gain access to systems. Overall, leap year bugs aren't just a nuisance. They pose serious risks to security, data, and operations. Properly addressing these vulnerabilities is essential to ensuring that digital infrastructure remains secure and reliable. So, how do we go about preventing these issues? For developers, the answer lies in testing and planning ahead. Modern software relies heavily on automated testing, and any system that handles time or scheduling should account for leap years. This might sound simple, but the sheer complexity of date calculations means that it's an extremely easy mistake for developers to be making. Over time, many date and time libraries have been improved to handle these cases, but bugs still slip through. Therefore, we recommend the use of static code analysis. As Tong mentioned, that's the process of examining source code without executing it to identify potential issues. Specifically, through CodeQL, teams can improve code quality, security, and maintainability before software is run. In this section, I'll be going over 2 of the most common leap year bugs that we had found, some examples of them, and work through an example of writing a CodeQL query to find all common versions of this flaw. As Tong mentioned, and this is just a full disclosure thing, Microsoft, which is our company, through GitHub, did acquire CodeQL a few years ago. We're not on their product team. We don't do anything in terms of sales or anything. We're just speaking to this because it's the tool that we use internally and is the static code analysis tool that we're most comfortable with. My aim in this part of the presentation is to talk about the capabilities that you would want in a tool and the things that many static analysis tools can do as well. Before we get too deep into it, we also should understand what an anti-pattern is. An anti-pattern is a common but counterproductive solution to a reoccurring problem in software design or development. It often seems like a good idea at first, but over time can lead to negative consequences like poor performance, increased complexity, or maintainability issues. Recognizing and avoiding anti-patterns is important for creating more efficient, scalable, and sustainable systems. Currently, the main usage of CodeQL is to find anti-patterns to flag. All of the queries that we write internally and the queries that are required by our company are based on anti-patterns that have been found by the public. For leap year, we had 9 anti-patterns that we were working to solve before February of 2024. These revolved around the addition of unsafe values, combination of date values that could be harmful, storage of values, and more. For this example, we're focusing on 2 of the existing leap year anti-patterns that are similar enough to kind of understand together. While there are other leap year anti-patterns we could have focused on, these are just the easiest to jump into and understand. Anti-pattern 2 typically occurs when a developer wants to add or subtract some number of years, typically 1, to a date, but does so using a multiple of 365 days. With the introduction of a leap year, these could cause those dates to be off by 1, leaving room for any of the security flaws that I was going over before. Adding 365 days to February 29th, 2024 leads to unknown behavior where the date could either normalize to March 1st, 2025 or back to February 28th, 2025. The leap year doesn't necessarily need to be involved though. Subtracting 365 days from July 1st, 2019 gives July 1st, 2018, but subtracting 365 days from July 1st, 2020 would give July 2nd, 2019, excluding the other July 1st. Anti-pattern 3 occurs in a similar manner when a developer wants to add or subtract some number of months, but does so using 28, 30, or 31 days. By not considering a leap year, they may be adding 28 days when in reality they mean to add 29. Similar examples, adding 28 days to February 1st, 2019 does give the correct date of March 1st, 2019, but adding 28 days to February 1st, 2020 gives February 29th, 2020, instead of the March 1st date that was realistically expected. This is the most common response. However, different packages in different date languages have different behaviors for overflow of days in a month. Some may throw an exception while others wrap to the next day, but since we don't always know the answer, that's why it is seen as an anti-pattern. Here are the 2 most basic examples of these anti-patterns in practice for JavaScript. For both, a new date object is created, and then a number of days is added as a constant using the setDate function. Each of these would be flagged by CodeQL for their use of 365 and 28, respectively. The correct solution in this case would be to use a proper datetime library rather than just doing simple constant addition like this. Now, for the actual writing of a CodeQL query, we'll be focusing on anti-pattern 2. Which, as said on the previous slide, looks at the addition and subtraction of 365 days. On the right is a sample file that shows some examples of the anti-pattern in practice. The first one shows the creation of the date, followed by an addition of 365 days to that date using the setDate function. The second one does the same thing, but does so putting 365 in a variable just to show how the data flow or taint tracking could work in this scenario. And the third adds 365 days to a new date object by creating the date object from a calculated timestamp. That one is specifically there to show why a simple control F wouldn't work. Random other ways of creating the same problem can always come up, and using static code analysis is really helpful to just grab all of those. Based on these samples, we have 3 alerts we would like CodeQL to find. Does anyone have any ideas what lines they would be on, if you can read the line numbers from where you are? If you could guess and see it from where you're sitting, lines 3, 8, and 12 should be the ones that are alerted, with the entire statement with the addition being highlighted. Based on this, we can begin the process of creating a query. As Tong mentioned before, I wanted to be touching on taint tracking. This is something that is absolutely necessary for this query. Tong explained data flow before, how it traces the flow of information from one part of a code to another. CodeQL taint tracking, on the other hand, focuses on tracking the flow of potentially dangerous or untrusted data, known as taint, within a program. It identifies the sources of untrusted input and then follows that data to determine if it reaches vulnerable parts of the system without proper validation or sanitization. Taint tracking is different than normal data flow in that normal data flow libraries are used to analyze information flow in which data values are preserved at each step, while taint tracking uses it to analyze information flow where data values could have tainted a different variable. For example, if you're tracking an insecure object X and the statement y equals x plus 1 pops up, a normal data flow analysis will highlight the use of x but not y. However, since y is derived from x, it is influenced by that tainted information, and therefore it is also tainted. In this specific query example, we need to be using taint tracking since we're following the path of an addition or subtraction of a value to the use of it in a date function. CodeQL makes taint tracking extremely easy, so all we have to do is identify the sources of the taint and the sinks, and CodeQL will find the paths between them. So since we're looking for the sources and sinks, we're going to be starting with the sources. To find the sources, we need to find the specific pattern that leads to the problem. In this case, it's anything that involves the addition of 365 to another value. We look for this because this pattern doesn't necessarily mean it's the full problem we're looking for, but it's necessary for that full anti-pattern to be found. Highlighted on the screen are the 3 examples of this from the sample code we're looking at. And if you see, the actual date object plus 365 doesn't actually prove that there's a problem until it's actually used in this sink. It needs to flow into a sink that makes up the rest of the anti-pattern. In that case, it would be the use of the setDate or the newDate function and constructor, respectively, that end up flagging the code. These are the same highlighted portions as we showed earlier on lines 3, 8, and 12, because these are the final portions of the code that should be alerted. Now that we know that, it's finally time to actually start writing that query. So to start, we first have to do the imports. We import in JavaScript, as that's the language that is currently being scanned. Each language has slightly different styles of query authoring, so that's a necessary line. The following 2 imports are dataflow and dataflow pathgraph. Dataflow allows for use of the dataflow and taint tracking modules, and pathgraph enables path exploration and visualization of dataflow through the code. Enabling pathgraph allows for the visualization from sources of taint to sink in an interactive manner. Finally, we import classify files to allow for the removal of auto-build and auto-generated files later on in the code. So now looking at the code, we can begin to build the parts necessary to find the sources. To start, each of these classes has the statement extends something. So in this case, it says class unsafe year arithmetic nums extends expression. CodeQL has built-in classes with methods that can be used. We usually end up extending the class that's most similar to the object we're trying to find. Resources that explain this more in depth are attached to the end of the presentation. First, we want to find all the places that there is a number 365. This is the first step in building the source, as there has to be addition involving the value 365. To do this, we create a CodeQL class that finds either the number 365 or 525,600,000, which is that timestamp value measured out. And then there's also the case that someone, when they're trying to figure out dates, does 365 times 2 or 365 times 3. Instead of just like adding years, they just multiply out for the number of days. So the third statement is finding any multiplication that does that. And it's a little bit of a complex looking thing, but it basically says that given a multiplication expression, if one of the operands in that expression is the integer value 365, it counts. When we run an evaluation of this class, the 3 orange boxes that are highlighted on the left would be found. Using the unsafe year arithmetics nums class, we can find any of the addition or subtraction that may be happening in the code. The next class, arithmetic year ops, begins by finding an addition or subtraction sign like the plus or minus. Then it looks for 2 possible options. The first is the most basic option, where there is a addition or a subtraction thing that's happening, and one of the operands of that is an unsafe year arithmetics number. The second case is that the unsafe year arithmetic number is stored in a variable. In that case, it looks for the addition or subtraction expression, finds that one of the operands is a variable, and then finds that that variable has one of those unsafe numbers stored in it. Using this arithmetic year ops class, we can find any of the possible sources of this sample code as seen with those blue highlighted boxes. And you can see how the orange kind of goes into that blue. Now that we have those sources figured out, we can move over to the sinks. The first sink possible is the setDate class. To find this using CodeQL, there's a simple class that can be made that looks for any callees that are specifically called setDate. Running this CodeQL class will find those 2 purple highlighted boxes. This one is a little bit more complicated, but still the exact same idea. In the case needed for this anti-pattern, the number 365 must be affecting the year value of that new date instantiation. However, when using a new date constructor, the year, month, or day can all be set. So our code needs to be able to specifically grab that year argument as a sink. To do this, we can make a class that has a characteristic statement that makes sure that it's a date, which we do with the get callee name equals date, and then have multiple other methods within it that can identify the year, month, or day arguments. Since each of those are always set at a very specific location, 0, 1, or 2 respectively, the code can look for the value at those specific arguments. Running this date instantiation core class finds the 3 pink boxes highlighting the new date, and then running get year arg specifically finds that red highlighted box. Are there any questions before we keep going on the source and the sink stuff? So it can also catch the correct implementation, which is also always one of the problems of static code analysis. What we try to do is we typically look for those false positives, so that way we can specifically gear them out. In this case, the correct way of doing it would not be to use like a set date like that with an addition. It would be to use a set year function, which does exist in the same class. So that correct version of it that's found with the anti-pattern and in the anti-pattern explanations online aren't going to be flagged because we don't look for set date specifically. Or set year, sorry. Most of the library packages that you can use for this stuff does actually already take care of that. The problem is usually when developers are doing it more manually because that's just the habit that we all have. Continuing on, now that we've had those, we can add them to the taint tracking configuration. This module exists in CodeQL to use the taint tracking capability. So we start out by making the characteristic statement of year data flow that just explains what this module is doing. And then in this case, it says finds where 365 is used in a year addition or subtraction. Then we have to override the isSource and isSync statements. And each of the source and sync have to be written out. In this case, the source is arithmetic year ops, as we found out earlier. So line 70 says that if an arithmetic year ops object exists, it could be a source, so save it as a starting node. In this case, it's, once again, all of those purple boxes. The next 2 lines remove all of the library and auto-build files that typically come along with making a JavaScript project, so that way we don't get an influx of results that we can't control. Within the sync predicate, we know that it either has to be a set date object or a date instantiation core object. So what this is saying basically is that if a set date exists, that could be a sync, so just save it as an endpoint. Or if a date instantiation core object exists, once again could be a sync, so save it as an endpoint. Behind the scenes, when we run this, CodeQL will look for any paths between those starting nodes and those ending nodes. And if one exists, that means there is a path from a bad start to a bad finish. And we have possibly found an example of a true positive for the addition or subtraction of 365 days. Now that all of that is done, we can finally write the select statement, and that's the true part of a CodeQL query. It includes a from, where, and select statement. The from statement chooses the variables that will be used in the query. The where statement defines the bounds of what would be chosen, and the select statement is the output of the overall block of code. Here, we say that given a source and a sink, where there is a year data flow with a path from that source to that sink, we can select those values with a message explaining the problem. This is similar to an SQL select statement, though some of the syntax is just weird and it's something you end up having to get used to, and you look at the references a lot. While I'm not running this live, it's really similar to how Tong's example from earlier was run. The alerts that are found are underlined in yellow on the left side of the screen, and that's what the code shows. And then below the actual query statement is what the alerts look like in terms of when you run them, the messages that you get. With the same blue lines that if you click on them, they would bring you to the correct place in the code. Now, at this point, we have a properly flowing query that will summarize the anti-pattern shown. So this example only shows this working on a 20-line file. How do we actually use this in practice? We use multi-repository variant analysis. Also known as MIRVA, this is a powerful tool for examining code over different repositories. MIRVA ensures consistency and highlights the impact of changes on each of the code bases. Here, MIRVA allows for CodeQL to be run on up to 1,000 repositories on GitHub from VS Code at a time. Leap year queries are really any queries that find problems, can be tested on large amounts of data to find a majority of instances of a security flaw. As a consumer or an external person, if you would want to use a similar process with MIRVA, GitHub has a CodeQL database for every repository that has enabled code scanning. This means that your queries can be run on any of your own GitHub code bases, and you can make them yourself and run them personally. And with that, we've reached the end. CodeQL and really static analysis as a whole are very useful tools for security and finding bugs before major events occur. Having something like this that allows for large code-based scanning and finding every instance or nearly every instance of a problem that can then be sorted and fixed is a tool that shouldn't be taken lightly. We've attached extra resources that can connect you to more about PQC and CodeQL as a whole. Please let us know if you have any questions. We also really quickly wanted to thank our team back at Microsoft for their help in finalizing this talk and all of their suggestions along the way. And here are all those resources. Are there any questions? So that's the nice thing with using like the taint tracking or the data flow things. It does show you every single step of that process and it would, unfortunately, it can't be run live because one of the problems with data flow and taint tracking and something that Tong brought up earlier, it is extremely slow. But when you were to run a data flow, it would actually highlight every single line that one of those happens on. So the way that this is showing up with those squigglies under the yearbad.getDate is that it highlights the argument of the final call. That is the problem. But with the data flow, it would show you where the 365 is, where the addition is, where the addition moves to throughout the process, and then finally where it ends up. And then the other issue is like stuff like with timestamps or if they're using like bigger amounts of days. Those were always the problems that we had with it. But I actually have not thought about Grodded before, no. Yeah. Honestly, I don't think... I will say it was not as hard to understand as it was to explain. But I don't actually know how close Copilot is. We just Microsoft as a whole has been working more to get Copilot more integrated into things, but especially with security, it's always like a little bit of an iffier statement. So that's actually more on the product side of things, which is the GitHub team, which we don't work with. But I believe there is an effort, as far as I know, but the bigger issue is more just like object-oriented code versus scripting languages have such different ways of writing languages that it's really hard for an like an AST tree to actually be able to like manipulate them the same way, which is why all of those languages end up being mixed up a little bit. Yes. I don't believe it's easy. However, I have met people who have done it. Do you know the answer to that one? Like extending it to a different internal language. I was incorrect. It only supports those several big languages. Yep, so that's exactly what we do. Typically, the life cycle process of this is running it like this. So actually, the way that I was running it when I was creating this presentation was all locally on a sample test that I had made to find false positives, true positives, whatever. And then we run it in a little bit of an environment to see how many false positives we find when we run it on a larger amount of code. And it's just a cycle until we get the false positives down to like less than, I think, like 5%. Okay, thank you so much.